Hi everyone, I am Dr. Kiran Raavi, working as an assistant professor in the Department of Electronics and Communication Engineering, MLR Institute of Technology, Hyderabad, India. Today we are going to discuss MOS capacitor, its operation, so that is depletion mode operation and inversion mode operation. Let us see the overview of today's presentation. So let us discuss introduction part of MOS capacitor and its basic structure, and then modes of operation, particularly depletion mode and inversion mode of operations, and we are going to study the characteristics of MOS capacitor, conclude with the summary. So we know what is MOS capacitor. MOS capacitor stands for metal oxide semiconductor. So this is the basic structure of MOS capacitor. It's a three-layered device. The three layers are metal, oxide layer, and then semiconductor layer. So a MOS capacitor comprises semiconductor body, substrate, an insulator film such as SiO2, and a metal electrode called gate. So this is metal electrode gate terminal. So oxide film can be as thin as 1.5 nanometers. So very thin layer of the oxide. So before 1970, the gate was typically made of metal such as aluminum. So hence the name metal, M stands for metal. After 1970, heavily doped polycrystalline silicon has been the standard gate terminal. It is used in integrated circuits, MOS transistors to store charges in the integrated circuits, ICs. So it is not used in individually. So it is used in the integrated circuits. So MOS capacitor. MOS capacitor used in MOS transistors. So the basic principle is the capacitance of MOS capacitor varies with voltage applied to its gate terminal, with the body typically grounded during this application. So capacitance of the MOS capacitor can be varied by applied voltage. So we have 5 modes. So today we mainly focus on depletion mode and inversion mode. So coming to the depletion mode of operation. So when a positive charge is applied, a negative charge is developed at the gate and polarization of SiO2 takes place. So if you observe, so this is the 3 different layers. So this is first layer, oxide layer. So this is first layer means metal layer. This is oxide layer, and the third one is, you can say, semiconductor layer. This is semiconductor layer. It may be P type or N type semiconductor. Okay. So positive charges. Now we are giving in depletion mode of operation, we have to apply the gate is positive and very small voltage we are applying. Positive charges of SiO2 repel the holes of the P substrate, and hence holes move down and depletion region appears under SiO2 layer. So as we know, like poles repel each other. So the positive charges of SiO2. So these are the positive charges of SiO2. These positive charges of SiO2 repel the positive holes in the P substrate. So the lower layer is P substrate. The majority charge carriers or majority charge particles of P layer are holes which are being positive. So they can get repelled by the positive carriers in the oxide layer. Depletion region is empty of holes, but it has an immobile charge in the form of negative acceptor impurity ions. Maybe depletion region is empty of holes, there are no holes, but it has immobile charge in the form of negative acceptor impurity ions. The negative charge of these ions known as depletion charge, and when gate voltage increases, depletion width decreases. So when gate voltage increases means negative voltage, and depletion width also increases, and thereby immobile depletion charge also increases. So the charge carriers, immobile charge carriers in the depletion region also increases when you increase the negative voltage at the gate. The change in the depletion charge with gate voltage results in depletion capacitance. So this is the basic principle in the depletion mode of operation. The capacitance of the MOS capacitor changes with the change in the depletion charge and gate voltage. So depletion charge changes with gate voltage and hence MOS capacitance also changes, and that capacitance is called transition capacitance in the P substrate. Depletion mode of operation, the capacitance of the depletion mode is given by CD is equals to epsilon A by omega D. So here epsilon Si, so see silicon, oxide layer. So oxide layer means dielectric material. So dielectric material constant is permittivity. So epsilon means permittivity. Epsilon, right? Permittivity of the dielectric material represented with epsilon. So hence epsilon suffix silicon into area A, and this is the width of the depletion region, because I already told you when gate voltage increases, negative value of the gate voltage increases, so then the depletion region also increases because charges, immobile charges are increases, so hence the depletion region increases. So the width of the depletion region also increases. So you can observe here. So this is the depletion region of width of the depletion region. So the depletion width is inversely related to your depletion capacitance. So that is given by depletion capacitance. If Vg further increases, depletion width increases, results in decrease in depletion capacitance. In turn decreases the MOS capacitance. So if you further increase this value, the depletion width also increases, and then correspondingly depletion capacitance increases. If depletion capacitance increases, the MOS capacitance also changes. So therefore, there is a decrease in the depletion capacitance. Depletion capacitance decreases. In turn, your MOS capacitance also decreases. So series combination of oxide capacitance and depletion capacitance gives the total MOS capacitance. And this is the series combination of oxide capacitance and depletion capacitance. So here that is given by CMOS. The MOS capacitor capacitance is given by C0 into CD by C0 plus CD. So this is the series combination. So when capacitors are connected in series, so we can write C1 C2 by C1 plus C2, right? So this is the depletion mode of operation. And in depletion mode of operation, we can also say that the minimum capacitance in depletion mode is given by CD minimum. Depletion capacitance, minimum depletion capacitance is given by epsilon A by WD maximum. So width of the depletion region, maximum width of the depletion region, and silicon material constant, that is epsilon, and area of the oxide layer. So that is given by CD minimum is equals to epsilon silicon into A by WD max. MOS capacitance varies with gate voltage in depletion mode, and hence it is voltage dependent capacitor. At one value of Vg, gate voltage, depletion layer width becomes maximum. Hence depletion mode capacitance becomes minimum on and thereby MOS capacitance also becomes minimum. So depletion, the negative voltage increases, negative gate voltage increases, the charge mobile, so that is immobile charge increases. So and then there is a increase in the depletion width. So when it is increases, that reduces the capacitance. Depletion capacitance decreases. When depletion capacitance decreases, obviously your MOS capacitance also decreases. And that is minimum MOS capacitance is given by, in terms of depletion capacitance and oxide capacitance, is given by C0 into CD minimum by C0 plus CD minimum, just like a series combination of this. So overall capacitance, minimum capacitance is given by this one. Now coming to the inversion mode of operation. In inversion mode of operation, when gate voltage is largely positive, so if you apply any positive voltage to the gate, the metal layer gets more positive and it causes strong polarization of SiO2. So here we are giving more positive value and large. And then due to this positive charge of SiO2 becomes sufficiently strong, it starts attracting the minority electrons from the P substrate. So if you further increase the gate voltage, positive voltage, then so positive voltage means, and minority charge carriers present in the P layer. So this is P substrate. In this P substrate, electrons are there, minority charge carriers, and they are attracted towards the oxide layer. So these electrons accumulate below the SiO2 layer, under SiO2 layer, which is called inversion layer. And whenever MOS capacitor is in the strong inversion mode, an increase in the gate voltage causes increase in the electron density. So there is an accumulation of more number of electrons under SiO2 layer. So the immobile charge of the depletion layer remains constant. So here the charge is in the depletion layer remains constant, and the depletion layer capacitance almost constant. So at a particular voltage of the gate, if you further increase positive voltage, so there must be some attraction of electrons in the P side towards the SiO2 layer, and that to some extent. So then after that it will be constant. So hence depletion layer capacitance is almost constant and disappears, and depletion capacitance becomes MOS capacitance only itself, and is given by CMOS, means MOS capacitance is given by C naught, oxide capacitance, that is given by epsilon A by Diox. So coming to the CV characteristics, capacitance across and versus voltage. So here it is the graph drawn between MOS capacitance and gate voltage. So we can take a capacitance, MOS capacitance on y-axis, and then gate voltage on x-axis. So if you observe, there are three different operating modes: accumulation mode, depletion mode, and inversion mode. So see here, if you observe, when gate voltage is negative, when Vg is low, negative, in this case, so we have a constant capacitance at a particular voltage, that is equals to C max equals to C naught. MOS capacitance is equals to oxide capacitance when Vgs is equal to negative. So that is called accumulation mode. And after that, when Vgs is positive, so that is depletion mode. When Vgs is positive up to certain amount of voltage, gate voltage, there will be a some increase in the capacitance, so sudden decrease in the capacitance in depletion mode. So you can observe the decrease up to some extent, and after that, so there is an inversion mode. So if you keep on increasing positive voltage, so if you keep on increasing the positive voltage, it reaches again, there is a linear increase in the MOS capacitance up to some extent, and after that it will be constant. And this is the basic capacitance versus voltage, gate voltage curve. So that's all about MOS capacitance characteristics. So today what we have learned, so we have started with introduction to the MOS capacitor and basic structure of the MOS capacitor and modes of operation, that is particularly depletion mode and inversion mode, as well as strong inversion mode also we have discussed. And we have discussed the CV curve, that is capacitance versus gate voltage curve, and how it will be, the capacitance changes with the gate voltage. So that's all for today, and next topic will be probably special purpose diodes. It comes under unit 5. Thank you.